The mind-bending paradox of the wheel paradox. This was proposed by the ancient Greek mathematician Aristotle. On a disk, there are two concentric circles of different sizes. When the larger circle rolls one full turn, the smaller circle also completes one turn. But the problem is that the circumferences of the two circles are obviously different. Why do they travel the same distance? For a long time, this question puzzled mathematicians. Although many explanations were proposed, none could intuitively explain the problem. It wasn't until more than 2,000 years later that Galileo came up with a clever approach. By analyzing polygons, he perfectly solved this problem. He simplified the two circles into polygons to roll them and applied paint on their edges to observe the traces of their movement. The traces of the larger polygon are continuous straight lines, while the traces of the smaller polygon are intermittent, leaving many gaps, as the number of polygon sides gradually increased. The gaps in the smaller polygon also gradually decreased. Then the source of the problem became clear. When two circles of different sizes roll, actually, only the larger circle is truly rolling, while the smaller circle in the middle follows the rotation of the larger circle, sliding as it rolls. In other words, the gaps created when the smaller polygon rolls are the traces of sliding. Simply put, the large circle rolls, while the small circle crawls along while rolling. Why doesn't a small ball get thrown off when placed on a spinning disc? Even if we give it a gentle push, it will continue to move in a circular path on the disc. But if we replace it with a coin or a toy car, they quickly fly off. So what exactly allows the small ball to stay steadily on the disc? We can observe that every time the disc rotates 7 times, the small ball rotates twice on the disc. According to the orbital period formula, no matter how we change the size of a solid ball, they always rotate in a 7:2 ratio from the side view. The small ball maintains a rolling state in place, but due to minimal air resistance, its rotation speed matches the movement speed of the disc's surface. So the small ball actually rolls uniformly in a straight line on the disc, similar to running on a treadmill, moving forward but staying in the same position. If we replace the disc with a smoother one, the ball will roll longer due to less resistance. In other words, ignoring air and disc resistance, theoretically, the ball could keep rolling forever. When we give the ball a push, because the disc's center rotates slower than its edge, the ball cannot match the disc's speed and deviates. When it rolls to the disc's edge again, the relative speed of the disc pulls it back toward the center. This repeated process creates the counterintuitive phenomenon of a ball continuously circling on the disc. Staring at it for a long time might just fry your CPU. This leads us to one of the most impossible forms, a classic visual illusion, the miraculous Penrose triangle. It looks like a triangle from the outside, with each angle seemingly a right angle, and the 3 beams connected end to end. Appearing incredible, but it does not exist in 3-dimensional space. What you see is merely an illusion created by spatial misalignment. Because your eyes are deceived, it naturally looks mind-bending. When you change the viewing angle, it becomes obvious. A famous variant similar to the Penrose triangle is called the Penrose staircase. It has neither a highest nor lowest point. Once you step on it, you enter an infinite loop, never reaching the end. In mathematics, the Penrose staircase is a classic geometric paradox. First proposed in 1958 by British mathematician Roger Penrose and his father, Lionel Penrose. Theoretically, no matter whether you go up or down the stairs, you will never find the highest or lowest step. For example, you may seem to go upstairs, but your actual height is continuously decreasing, and vice versa. This so-called visual illusion reveals the limitations of human visual perception and the subjectivity of sensation. It challenges our understanding of space and depth, forcing us to reconsider perception and cognition in the real world. It also expresses a philosophical idea. In some situations, our perception can mislead us, and we cannot rely solely on intuition. The Penrose staircase not only appears in art, but is widely used in psychological research as a tool to explore perception, visual illusion, and cognitive processes. Studying the Penrose staircase helps humans better understand their own perception mechanisms and reveals how we perceive the real world. Have you heard of the Moebius strip? It's an endless loop with no end. You can make one easily from a strip of paper, and you'll discover its amazing properties. Simply twist the paper strip and join the ends. This seemingly simple loop hides extraordinary phenomena. If you cut along the middle, you will find it does not split. Instead, it becomes a larger loop. If you cut along 1/3 of the width, after 2 cuts, you return to the starting point, forming a larger and a smaller interconnected loop. The large loop's circumference is twice the original, while the small loop's circumference remains the same. If this existed in the real world, walking along the middle without crossing the edges, you would touch both sides and return to the start. With a normal circle, you could only touch one side. The other remains unreachable. Designers often incorporate embossed strip elements in rings, symbolizing the cycle of life and eternity. Meaning no matter where you start, you will ultimately meet again. The starting point is you, the end is also you, and in the end it's still you by my side. This brings us to a mathematical problem about life and death, the Josephus problem. During ancient Rome, a Jewish general named Joseph and his 40 soldiers were surrounded by the Roman army. Unwilling to be captured, they agreed on a suicide plan. First, everyone forms a circle. Starting from position 1, they count clockwise, killing the next living person, then continue killing every second person, until only one remains to end his own life. The process is like a deadly circle game. But General Joseph did not want to die. He wished to survive until the end and surrender. The question is, where should he stand to survive? With few people, the problem is simple. If there are 8 people, the person in position 1 survives. But if the number increases to n, how to choose? By experimenting, a pattern emerges. If there are 3 people, position 3 survives. For 41 people, position 41 survives. For 53, position 53 survives. Compiling the results into a table, we see that to survive, one must avoid even-numbered positions. Position 1 has a very high survival probability, corresponding to numbers 1, 2, 4, 8, etc., which are powers of 2, following this rule. If there are 16 people, after 3 rounds of killing, position 1 survives. So, when the total number is a power of 2, the initial position is guaranteed to be the last survivor. Now, if there are 11 people, we write 11 as 2, 3 plus 3. The survivor's position is 3, 2 plus 1 equals 7. If there are 13, write 13 as 2, 3 plus 5. Then 5, 2 plus 1 equal 11. Hence, a general formula. If total x equal a plus 2n, survivor y equal 2a plus 1. Thus, regardless of the number of people, we can easily determine the survivor. In the original scenario of 41 people, Joseph can write it as 2, 5 plus 9. Then 9, 2 plus 1 equal 19. So standing at position 19 ensures survival. Have you learned this yet? Why does a football bend strangely in flight, defying physics? In 1997, Brazilian footballer Roberto Carlos kicked a free kick that shocked the world. The ball curved impossibly around the wall. The trajectory resembled a banana, hence called a banana kick. This sharp curve is explained by the Magnus effect. When the player strikes the ball slightly below the center and to the side, friction causes rapid spin as the ball moves through the air. The airflow on one side accelerates with the rotation, lowering pressure, while the opposite side slows airflow, raising pressure. The pressure difference curves the ball from high to low pressure, forming a beautiful arc. To demonstrate, experimenters spun a basketball and threw it from a 100-meter dam. The ball did not fall straight, but followed a curved path to the lake. The Magnus effect also applies to other sports balls and in aviation or ships. Since the 1980s, cylindrical ships use rotating cylinders to generate forward thrust in crosswinds. Flight enthusiasts also build simple cylindrical aircraft, using rotation to maintain prolonged flight. Now, have you learned to kick a perfect banana kick? Is the world you see truly real? Suppose someone has been unable to distinguish blue and green since childhood. He sees the sky as green, grass is blue. Adults taught him the sky is blue and grass is green. So, even though his perception differs, he uses the same terms as others. Although he confuses blue and green, he calls green sky blue and blue grass green. Communicating without problems, how can you prove you are not this person? This is Dalton's color blindness paradox, proposed in the 18th century by English chemist John Dalton. It challenges our perception of color and raises philosophical questions about epistemology, reality, and individuality. If everyone's sensory experience is unique, is it possible that the objective world we see is not the same? How then do we define the essence of perceived things? For the color-blind, language symbols may represent the true color world. Since no one can see another's world, who can be 100% certain their perception is the real world? Is my vision failing, or are mathematicians crazy? 0.999 repeating equals 1. Let x equal 0.999. Then 10x equal 9.999. Subtracting x gives 9x equal 9, so x equal 1. It seems unbelievable. Alternatively, if you plot 0.9, 0.99, 0.999 on a line repeatedly, the smallest point on the right approaches 1 by the density of rational numbers. There is a rational number between any two unequal rationals. So 1 must be that point, hence 0.999 equals 1. Mathematical proofs, including by Euler in 1770. Validate this counterintuitive conclusion. Though debated for centuries, many still resist believing it. Mathematical perfection carries a subtle eeriness in reality. How terrifying is antimatter? Why could a momentary reaction easily destroy a city? In 1928, British physicist Paul Dirac derived the Dirac equation, combining Schrödinger's quantum mechanics with Einstein's special relativity. But it allowed negative solutions contradicting physics. Removing them caused mathematical inconsistencies, so Dirac boldly predicted antimatter. 4 years later, American physicist Carl Anderson observed positrons in a cloud chamber, confirming antiparticles with the discovery of antiprotons and antineutrons. We realize that all fundamental particles have corresponding antiparticles, which can form antimatter. In our universe, if there are matter, planets, and galaxies, there must be antiplanets and antigalaxies. When antimatter meets matter, complete matter-energy conversion causes catastrophic annihilation, releasing immense energy and high-energy radiation. 0.5 grams of antimatter releases as much energy as the Hiroshima bomb. 1.5 kilograms equals the Tsar Bomba, the most powerful explosion in human history, affecting a 35 km radius, due to immense energy potential. Some countries invest heavily in antimatter weapons. However, antimatter does not naturally occur. Producing even 1 microgram costs about $6 billion and requires highly controlled storage. Besides weapons, antimatter could fuel spacecraft, producing hundreds of times more thrust than regular fuel, allowing travel to Mars in 1 month versus a year with current technology. Yet as a weapon, it is a double-edged sword, potentially catastrophic. Future scientific advances will discover more uses for antimatter, driving technological progress. Can you guess which ball reaches the finish line first? You'd likely choose the straight line, but it's actually a brachistochrone curve. Why does the principle the shortest distance between 2 points is a straight line fail here? In 1638, Galileo noticed a strange phenomenon in acceleration experiments. 2 balls of equal mass from the same point. The one on the curve always arrives first. Among countless curves between 2 points, which is fastest? This simple question eluded Galileo his entire life. 58 years later, Swiss mathematician Johann Bernoulli found the answer after extensive experiments, issuing a challenge to the scientific community, attracting many mathematicians and physicists, including Isaac Newton. Surprisingly, Newton solved it in just a few hours. He discovered that the fastest curve is a cycloid, the path traced by a point on the circumference of a rolling circle. An interesting fact, if several balls of different heights are placed on the cycloid, they all reach the end simultaneously. Thus, the farthest looking path is not necessarily the slowest. Choosing the right path ensures no departure is ever too late.